Welcome, everybody, to Standing for Truth. My name is Donny Budinsky, and it is a privilege to serve as your host for today's valuable program. We're joined by Michael J. Oard to tackle some of the strongest objections to flood geology. That includes river channels, paleosols, cross beds, chalk, limestone, burrows, and much more. Mike is going to walk us through beds, briefly exposed diluvial sediments, and demonstrate how these supposed challenges can be addressed within a catastrophic Genesis flood model. We have a lot to cover, and I am excited to see what Mike has in store for us on this important topic. Mike, certainly not your first time here, brother, on Standing for Truth. You've been a blessing over the years. I'm constantly referring back to our past programs where we've engaged in countless hours worth of Q&A, answering objections, and engaging criticism. So, Mike, how have you been? And tell us, how's your summer coming along?
Oh, it's going very fast. But I'm home most of this summer, and mostly home until my next event in June. So I get to do research for many, many months.
Well, that's awesome.
Which is my passion.
Well, there's certainly unlimited research. We were talking backstage. For every question that we answer, 10 new questions arise. And so it makes it fun being a creationist, that's for sure. Because if we had all the answers to everything, then what would we be doing, essentially?
Right.
Mike, this is going to be great. So to the audience, we've already got a good mix of critics and non-critics. We will be engaging some of the strongest objections to flood geology on the screen. I do want to encourage people. Michael J. Oard, here's a link. My chat mod, Doki Doki. Appreciate it, brother. Hope the coffee is hot today. We got a link to Mike Oard's past presentations, a link here to creation.com, where you can find countless articles where Mike, over the years, has interacted with so many different topics related to origins. And of course, Mike's website here, michael.ord.net, where you can get into information on the flood and the ice age. Now, for those who might be unfamiliar with the channel and Mike Oard, I do want to give a brief introduction or bio for people. And so Michael has a master's science degree in atmospheric science from the University of Washington, and is now retired after working as a meteorologist with the U.S. National Weather Service for 30 years. He has researched and speaks on the compelling evidence for Noah's flood and the ice age that followed, and how the incredible woolly mammoth, we've done an entire program on that topic. I've also got Mike's book on that issue behind me, connects to biblical history. Michael has published many papers in his field in widely recognized journals, and has written An Ice Age Caused by the Genesis Flood, Ancient Ice Ages or Gigantic Submarine Landslides, the Missoula Flood Controversy. We've also done a whole program on that, and the Genesis Flood and the Frozen Record. I do also want to mention, honorable mention, I've got your one of your more recent books behind me that you wrote with Dr. Rob Carter, Geology 101. He is also author of Frozen in Time, The Weather Book, and Life in the Great Ice Age. He serves on the board of Creation Research Society USA and lives in Montana. Okay, to the audience, for those joining us, the structure for this program, we are going to be handing it over to Mike. He has a presentation for us on the topic. While he's presenting, I will be taking audience questions, objections, challenges. I'm sure I'll be having my own questions. And so once he's done with his talk, we'll jump into some free-flowing discussion. So with that, Mike, I am going to give you the floor, brother. I've got your slides up on the screen. It says the beds model, explaining associate features in Noah's flood. And so the floor is yours. Take as much time as you need.
Okay. Thank you. You see my topic, just like Donnie has said. BEDS is an acronym, stands for Briefly Exposed Diluvial Sediments. Diluvial is another name for the flood. So this stands for freshly laid flood sediments that are briefly exposed. And I'll have some diagrams to illustrate this. And why are there beds in the flood? Because sea level oscillates during the flood. It's just not going up gradually and going down gradually. But it'll oscillate due to 5 mechanisms, at least 5, which I will list soon. So a local drop exposes flood sediments, and a rise will cover up what was occurred on those flood sediments and preserve them. Now, I mainly wrote about beds because of dinosaur tracks or eggs and scavenged bone beds, of which there are millions of dinosaur tracks and dinosaur eggs. They find new locations every year globally. So that was why I wrote about this. But here's kind of a illustration of how it works. This is a block diagram. Think of this as kind of an area that goes out maybe 100 or 200 kilometers. We're just taking a slice through it. Anyway, at time T1, there's the top of the sediments, and you're having rapid sedimentation. In fact, these areas of dinosaur tracks and eggs are generally in areas of thick sediments. But at time 2, you've deposited a lot more sediments, but by time T3, even more, to the point where the top of the floodwaters and the bottom of the floodwaters becomes very shallow. And it's prone to local falls and rises in the level of the floodwater, like in this. So you have a local drop in the flood level, and it exposes a freshly laid bedding plane. And then you have a rise that covers up what was laid on those or occurred on that bedding plane to preserve it. See, one of the big problems of these associated features are delicate. Dinosaur tracks are very delicate, and all the most of the other features on these beds. So you got to preserve them. That's a key thing. And so the flood is able to do that. Anyway, there's 5 mechanisms to cause beds: tectonic uplift or subsidence in an area, tsunamis, of course, lunar tides, which oscillate twice a day, crustal shifts far away, and flood current dynamics. I will briefly go through these. This is just a schematic between day 70 to 77. And this is oscillations from local tectonics. You can have the level of the floodwater go up and then go down. And you might expose the sediments for maybe up to 2 weeks or more during as the area is coming up. Local upward tectonics. And then from tsunamis, you're going to get a lot of oscillations in that 1 week period. And I'll have some illustrations on this one. And then, of course, lunar tides, they're going up and down. This floodwater are generally going up. And so you're oscillating them by lunar tides, a third mechanism. And then far away, say a third of the way around the Earth, tectonic movements will cause waves in the floodwaters that will propagate long distances. That will cause rises and falls in the level of the floodwaters. And then there's one called current dynamics. This is where sea level will oscillate due to the dynamics of the current. This is from Barnett and Baumgartner, which they did a model on what's called shallow water, doing the shallow water equations. By shallow water, they mean 1,000 meters or less. And on that shallow water, by the spin of the earth, Coriolis effect, you spin up huge currents on that shallow water. And the dynamics of those currents cause the water to pile up in ridges and fall in troughs, exposing flood sediments. Like here is one of Barnett and Baumgartner's illustration in shallow water. And as you see, the currents snake around in ridges and troughs, just kind of like the atmosphere. And in troughs, the actual level of the floodwaters falls and can intersect the bottom. That's that brown area you see in that illustration. And these currents, from their computer program, they became as high as 70 meters a second, which is huge. That's probably around 140 miles an hour. And so all this has a lot to say in the flood, but that's beyond the scope of this presentation. So this is kind of a summary of all of them. And this is kind of a poor diagram for a week in the flood. There's a flood. You can have oscillations at various scales, but I generally gave 2 oscillations there, a major long wave and smaller short waves in the box. But in reality, it would be very chaotic with short, medium, long amplitude waves, but it's a general rise in the flood level. So here's a few illustrations that my artist did. This is, remember, this is designed to account for dinosaur tracks, eggs, and scavenged bone beds. Anyway, this is from tsunami. A tsunami, of course, is going to hit the shoreline hard, but as it's flowing inland, it's going to slow up and it's going to leave a layer of sediment. It'll destroy it near the shoreline, but so the tsunami hits and destroys part of the shoreline, but then just rolls up and over, covering up, you see dinosaur tracks and a dead dinosaur, so that they're preserved to this day. And then the flood waters locally go down, leaving something like this. This is just a schematic. You got to think of the beds over maybe 100 to 200 kilometers laterally in one dimension. And here's another one where they lay eggs, make tracks, and on a large area of exposed diluvial sediments. And then the flood level rises, covers up and spreads a layer of muddy sediments or sand on top of all these features. It could drive the dinosaurs off that area, or in this case, my artist had them kind of hanging on for dear life. Either way, you have a lot of options. And this illustrates how you can form the dinosaur tracks, eggs, scavenged bone beds at multiple horizons in an area, which is what you see. So they can do it again, and it can repeat itself. Remember, think of this as a huge, wide area. So that's what it's designed to do. And in my book, which I will show at the end, I mentioned associated features. When you have briefly exposed diluvial sediments, you're going to have other features. I did not emphasize these in the book, but I did mention them and say a little bit on them. But these are the 7 features I mentioned can occur on these beds. True mud cracks. It only takes a day or a little more for a mud crack to form, a true mud crack. So you can have true mud cracks in the flood sediments. Raindrop imprints, of course, because it rained 40 days and 40 nights. Then the rain let up. Clear today, 150, the general peak of the flood. Bird tracks, of course, would be easy to form on beds. Coprolites and paleosols. I'll be getting into that topic a little more. You can have burrows and tracks of invertebrates. You can have aquatic and social insect features. So anyway, here are a few pictures of these. This is taken from Utah, a display of true mud cracks. By the way, mud cracks can form underwater called syneresis or diastasis cracks caused by chemical changes. But in this case, actual true mud cracks can occur on these beds. And here's a picture of them at a dinosaur location in Utah. And here are burrows, invertebrate burrows. In fact, they look like raindrop imprints, but they claim they're vertically burrowing invertebrates. So yeah, you can have those on beds. Bird tracks, of course, no problem there. So Dr. Feldman emphasized these 7 features on his podcast that I looked at. And some of them I've mentioned already and as associated features, and some I haven't. And there's the list right there. And I've mentioned tetrapod tracks, dinosaur tracks, and other vertebrates. Paleosols, of course, I'll get into that. A little more raindrop imprints. I totally agree with Dr. Feldman that these are true raindrop imprints, even though they can be copied by gas or fluid escape features, but there's ways to tell the differences. Valleys in sedimentary rocks, which I'll get into, valley meanders in these valleys, coal, etc. So paleosols. They were once considered rare and now common. I might add that Peter Klevberg and Rick Bandy, who's a retired soil scientist from Great Falls, Montana, and sometimes I, have gone out and looked at paleosols. One thing they found is a lot of times it's very difficult to find what is considered a paleosol where they claim there's one. And we analyzed paleosols in what's called the Kennedy Drift, just east of Glacier Park. And they weren't we couldn't see any evidence of paleosols, but that's what they claim, with multiple ice ages, I might add. Anyway, they were once considered rare and they're now common. The uniformitarian worldview says they should be common, and they should, if uniformitarianism is true. One outrageous example, I think, is a claim of 87 paleosols in 143 meters in Badlands National Park by Ritalik. He's the main researcher in paleosols. And there's several ways to get a paleosol. Dr. Feldman said that hydrothermal flow mechanism could do it, but it's only local. And that he said there's organic horizons. Well, all that is true. There are some. And anyway, in the flood, though, hydrothermal flow could cover a large area. And if the hydrothermal flow comes into the floodwaters, it can spread chemicals and heat and over an area and chemically change the sediments that would look like a paleosol. Anyway, this is Badlands National Park. Ritalik said there's 87 paleosols here. I find it very hard to see any of them. And when you look at the kiosks around there, here's one right here where they show the animals based on the fossils found in Badlands National Park. There's relief, there's water flowing, etc. But do you see such features? These are flat laying one after another with little or no erosion between them. and the environments, to me, don't show up. This is very similar to like the walls of Grand Canyon, where over 250 million years, the Paleozoic is deposited, but it's one layer flat on another, or mostly flat with little or no erosion. There are little signs of erosion, like little parabolic scours, but that's all. Anyway, this reminds me of that, and it's typical of sedimentary rocks and sediments globally. Now, these badland fossils are volcanic clastic reworked sediments. A lot of evidence of volcanism in the western U.S. So uniformitarian paleosol problems. I made a case that they're commonly missing the A horizon or the organic horizon. And if that organic horizon actually decayed, which is what they say it did, you should find, I would think you'd find pollen where it used to be. And as it's buried, it's in an anoxic environment and should be, you should detect a residue of the organics in that if it's a true soil. Our soil scientists hardly ever sees any evidence of ever, when they've examined paleosols, of a nice soil, can't think of the wording, horizons. You practically always find a clay layer or a carbonate layer that's said to be from the B horizon, and that can just simply be a clay or carbonate layer. Also, there's other exotic features claimed: slicken sides, blocky beds, root casts, etc. But we found that these are equivocal. Anyway, they're going out in September in the southeast Montana, and they hope to get some good examples of what are considered paleosols. Anyway, here's a quote that the A horizon or the organic horizon is rare. This is from Birkeland in Soils and Geomorphology. An A horizon in a buried soil might be useful, but the organic matter is usually so depleted that the A horizon is seldom recognizable on either color or content of organic matter constituents. As far as our explanations, I've already given a hint. Acid rain. A lot of volcanism during the flood, you're going to have tremendous acid rain that can fall on beds and do chemical changes. And diagenesis changes the chemistry during burial. Hydrothermal flow either within the sediments or coming out of the sediments onto the floodwaters and spread pretty far horizontal, not local, but considerable horizontal distance in the flood. And raindrop imprints. Here's a picture at that site in Utah. Let's see, you can't see them very well, but they're little pock marks here and there. Anyway, I've done some analysis of raindrop imprints. Raindrop features favor non-mud rocks, coarse grained sediments. They can be elliptical because of the wind. The pit size is variable, generally from 5 to 20 millimeters. They have a depth to diameter correlation, and spattering is common. Now, gas and fluid escape structure features can mimic raindrop imprints. And that favors mud rocks because you'd have a lot of gas and fluid that could form probably due to organic decay in the mud rock. And they first form a convex bulge like this as it comes up. Then a lot of times it collapses in the middle. And if you see a vertical section, it has to penetrate several layers. And sometimes it forms linear arrays, and they do not have spatter. I conclude that raindrop imprints are common throughout the geological column, and they easily form on beds. but beds preserves them when the floodwaters rise again. There are also many reports of raindrop imprints in the Proterozoic and Archean that meet the requirements. And I believe these are true raindrop imprints. And since rain you wouldn't expect rain on sedimentary rocks until the flood, I have come to believe, among many reasons, that the Precambrian sedimentary rocks must be from the early flood. Anyway, that's controversial within creationist circles, and so that's one of my many reasons for saying that. But I agree with Dr. Feldman on that one. Coal can form by beds. The uniformitarian peat swamp theory has numerous problems. In fact, creationists on websites and articles have, and even I've written a bit about it, show these problems. The worst problem is that in a peat swamp, you have to, the organic matter must not oxidize, and it has a high porosity. So to form a layer of coal, you've got to compress the peat. They claim a 10-to-1 ratio, but I have a feeling it's a lot higher than that, maybe 20 or 30-to-1. But anyway, we'll say 10-to-1. So to form a coal seam, that's, say, like in the Powder River Basin of my state and northeast Wyoming, where you have some coal seams that are 60 meters thick. To get that coal seam, you'd have to have 600 meters of peat. And the peat has to be almost pure because these coal seams are pretty pure. You can't have any plastic material getting in there. Now, they do have some volcanic ash material, but not a lot. So that's one of the main problems with the peat swamp theory. Also, you find vertical trees associated with coal seam. Some trees are actually upside down, which could form in the log mat model. And you can relate coal to the beds model because there's dinosaur tracks on coal seams in Colorado, Wyoming, and Utah, the United Kingdom, and Queensland, Australia. And so I think that's the key to explaining the origin of coal in the flood. And what it implies is that log mats, which I'm discovering could be very thick, are suddenly beached as the flood levels drop, and they get beached on beds. And then as the floodwater rises, you pin the sediments down, and a lot of times these tracks have sandstone. The dinosaur tracks and coal seams are sandstone, indicating pretty fast covering by water that pins the log mat down and buries it, and the pressure and the heat turn it into coal with time. The origin of coal actually, I believe, defies uniformitarianism. This is one of many quotes I can gather, but this is the shortest one. Unfortunately, scientists know very little about the processes involved in the turning wood into coal. From Life in Amber by George Poinar. So here's an illustration of how you form coal and connect beds with forming coal. And you got to think of this as huge horizontal areas. Many coal seams cover huge areas, I might add. The Powder River Basin, they can be 150 miles in a general north-south direction and about 40 miles east-west and up to 60 meters thick. And there's a report where I'm working on this, by the way, 47 coal seams in the Powder River Basin, some small, some huge. But anyway, you have a local drop in the flood level. Dinosaurs walk on top of it, somehow make tracks. By the way, the tracks are pretty shallow, surprisingly shallow. to those that have described them. And so they're perplexed because they should not be shallow on a peat swamp, by the way. They should sink deeply. But this is probably pretty compressed vegetation. And so the tracks they make are fairly shallow. And then you have a rise in the level of the floodwaters, and it puts sediment over the vegetation, turning it into coal. Anyway, by the way, I thank my artist, Melanie Richard, for all these schematics and diagrams. By the way, this is kind of a side issue, but floating log mats in the flood can solve other geological mysteries. I might add, in the flood, based on the amount of coal, we probably had, I've estimated 10 times the amount of carbon in the biosphere before the flood as after the flood. Now, I've since found out that needs refining, that figure. But regardless, it looked like it probably a very lush environment, huge amount of trees and plants. And in the flood, you rip up a lot of that. And a lot of it's going to be floating on the floodwaters. And so log mats moving on the floodwaters and even after the flood can solve the following geological mysteries. They can form polystrate trees. In other words, as some trees as they can sink vertically into the sediment. It can explain the Yellowstone fossil forest in that you have the trees sinking while the bottom is being filled in with these huge lahars of volcanic material from Eocene volcanism that covers 9,000 square miles, might add, and piled up to 6,000 feet thick before erosion caused a relief of 4,000 feet. And so you can explain the Yellowstone fossil so-called forest by the log mats. Also, you find a lot of paleoflora sites. For instance, Alaska has a lot of them, and they have conflicting climatic interpretations. You have plants based on macrofossils and pollen from warm climates next to the same thing from cool climates. For instance, this is the case in Yellowstone fossil forests. The forest material based on the tree and the pollen give you about 200 species of trees that originate either from a warm tropical climate or a cool temperate, all together in the same layer. And this is rather common at paleoflora sites, which there's numerous paleoflora sites around the Earth. Also, you can form isolated insect fossils where a lot of insects and other creatures would be floating on these log mats, and a lot of times they would die and sink and get deposited in sediments. The same with insects in amber, because amber is caused by this tree resin that is caused by trees being cut and broken up, and what you'd expect on log mats. So insects can end up in the amber, or with no insects in amber, but amber will sink eventually, and the insects in the amber, and get deposited in sediments, and then the heat of the sedimentation can turn the resin into amber, which is a fossilized resin. And by the way, I might add that this amber forms in a marine environment, and there's a lot of aquatic creatures found in amber. So amber has a lot of mysteries, which I believe the log mat model can explain. Then after the flood, you still have these log mats floating around, and you can result in, you can move animals from one point to another that after the flood's over with, like mammals, they propagate from the mountains of Ararat, spread. Some of them can end up on a log mat and be transported sometimes across oceans. And I believe this can explain a lot of biogeographic mysteries. So anyway, by the way, many of these topics I've mentioned are also research topics that need to be fleshed out more. If you want to know more about a log mat solved geological mysteries, I've written an ebook that you can get on the CMI website. There's the title. Unfortunately, it's an ebook, and hardly anybody reads creationist ebooks. So, anyway, that's where you can find this information. Anyway, let's get back to valleys, which Dr. Feldman especially emphasized. Now, this is from my 2011 book, where I knew about valleys and sedimentary rocks. And by the way, so did a lot of other creation scientists. I asked John Whitmore if he thought there were valleys and sedimentary rocks, which he said, yes, definitely. Anyway, here's a little schematic of how they would form. And remember, I'm thinking of dinosaurs. Anyway, you cover up dinosaur material, and then the level of the flood waters is falling, laying sediments down on a layer of dinosaur material that's buried. And then finally, you can channelize from the exposed beds. You can channelize, forming valleys like this with fossils in the valleys. And so this was from 2011. But this model has a lot of potential to explain other features. You don't necessarily need to have the same fossils in the valleys as you do in the sediments around it. You can have new ones, different ones that come in from farther away. But anyway, there's a lot of potential with this idea, forming valleys and sedimentary rocks. And I'm going to talk a little bit about valley meanders. This is probably one of the most challenging things that Dr. Feldman presented, which I have no problem. I don't mind being challenged. From a 3D view of valleys in the sedimentary rocks, they show meanders. I believe they can occur at the end of flood valley cutting. The way this would work is you're cutting the valleys pretty fast by channelized flow. As the flow gets down, you can go from eroding to a grading, being depositing sediments, and you have a huge amount of sediments available from the erosion, and you can cause meanders in all this, I believe. And in one of the papers that Dr. Feldman mentioned, they note a lack of tributaries to the valleys, which were said to be unexpected. Well, yeah, I wouldn't expect too many tributaries if these were formed by flood channelized runoff on a beds. And you can rapidly grade because meanders today are formed slowly. It's because a lot of times there's not a lot of sediment in the rivers to form the meanders, and the beds are a lot of times hard. I mean, the sides, the banks. But in this model, you'd expect the banks to be soft. And so, and with a lot of erosion, you can erode from the banks and from the very middle of the valley. So I can see a grading meanders should be able to occur rapidly. I'd like to find an analog for this. It's possible in some areas where they breached a dam. I'll have to look into that more. And here's the quote from Maynard, Feldman, and Always, 2010. None of the incised valleys have a dendritic drainage network. They mostly have straight to gently sinuous edges. So I think that's because it's not a normal dendritic drainage channel, but formed in the flood by channelized runoff. And this is the book I was telling you about where I wrote about this stuff. 2011, Dinosaur Challenges and Mysteries. It has a different cover. It's got a soft cover now. This is the hard color, but the subtitle is especially the real title. And by the way, these dinosaur challenges and mysteries were challenges to secular mainstream scientists also. They have a lot of dinosaur challenges, even though you might not know that. But I also dealt with our main challenge, which is how does the Genesis flood make sense of dinosaur evidence, including tracks, nests, eggs, and scavenged bones. So that's all I have, and I'll turn it back to Donnie for questions and answers.
Mike, excellent job. That flew by. Some
It
great
did.
answers. I blinked and it was over, but that speaks to how good it was. It's always fun to engage challenges and address criticisms. We have a lot of engagement in the chat, so that'll help us continue or expand on this discussion. If you want to come back and see me, where I can put some of these questions up on the screen for you to see, you can.
All right.
There we go. Good to see you again, Mike. Great slides. I may have to borrow some of those visuals that one of your friends put together explaining beds, because I find that helpful, especially for people that are new to this. Briefly exposed diluvial sediments. And so perhaps I can start with a clarification on the paleosols.
Okay.
You were pointing out that you've been in the field. You've looked at areas that are claimed to represent ancient soils, basically.
Mm-hmm.
But you had a difficult time identifying that which proponents of evolution have identified as paleosols. Is that right, Mike?
That's correct. But I've not been out near as much as my geologist friend Peter Kleberg and the soil scientist Rick Bandy from Great Falls, Montana have. And they're continuing to go out. They're going to go out in September into southeast Montana. And they went out last year, and the locations didn't show hardly anything. So they were really perplexed on that. But they're going out. They think they found some good ones from the literature in southeast Montana. So in September, I hope they find some and analyze them really well. That's what we need, is some good examples to analyze.
Right. And so if I understood correctly, a piece of your response there to so-called paleosols with the beds model, you'd have sediments on the planet that are exposed for a little while.
Yes.
And then are they chemically altered during that time?
They can be chemically altered by acid rain.
Yeah.
When they're exposed, but when they're diagenesis, as you pile up the sediments, can cause changes, chemical changes, and also hydrothermal flow can add heat and chemicals that can make chemical changes to a sediment.
And so those sediments that are altered chemically through acid rain and other means during that time period when those sediments are exposed during the flood, those would then give the appearance to deep time proponents that these are ancient soils representing lots of time, even though that these are simply sediments that were exposed during the flood and altered to give that same kind of appearance.
Yes, that's what I've come to believe.
And then in order to differentiate between our interpretation of these sediments, which they are interpreting as paleosols, what differentiating piece of evidence between our interpretation and the evolutionist interpretation, like Dr. Howard Feldman, who I see in the chat? Howard, feel free to send in your questions or Objections. Is there a feature we could point to, or a way to distinguish which explanation better fits the data?
Well, you'd expect some evidence of an organic horizon if it's a true buried soil. By the way, there are true paleosols. During the Ice Age, there are features that covered up Indian remains in the Midwest, covered up the soils also. And so they do exist, or landslide deposits coming out onto a soil, and you bury it. But the material deep down, that I would question. And I think that I would claim they're just a regular clay or carbonate horizon. That seems to be the main features. The claim of a B horizon. You have an A, B, a C horizon, and so the B horizon could just be a clay but altered. It could be chemically altered, so that they would point that out to as being a paleosol. So that's what I'd look for: the lack of or organic horizon. By the way, some of these other organic horizons could be called A or O, or there's another designation for them in the soil science. And so lack of A horizon and just simply a clay or carbonate layer or some other iron rich layer or something like that. So that'd be the difference. You don't see the regular horizons going from A to B to C.
That answer is helpful. And I have a follow-up question, but perhaps before I get to that follow-up question, to help people in the audience, because you mentioned, so a couple things here I'll clarify with you. There are true paleosols formed during the Ice Age, so the post-flood Ice Age. There are differing views on, within the creationist camp, I guess, how we would explain the Ice Age. Was it rapidly during the flood, or post-flood, which is probably the most common and best model explaining the Ice Age? But right here, Drosophila, when does the Ice Age occur in Mike Oard's model?
Well, right after the flood. And I think I have a podcast on this.
A very detailed one.
And so it's based on two mechanisms from the flood. A lot of volcanism, spreading volcanic aerosols into the stratosphere. They get trapped there for 1 to 3 or more years, depending on how high in the stratosphere the volcanic material goes. Also, volcanic ash on the land has a high albedo. So you're going to cool the continents by these mechanisms, but the water is going to be warm from all the volcanism, and the warmer the water, the more the evaporation. So you have cool continents and heavy evaporation from the ocean. They get caught in storms and dumped on the cool continents. And because of all that warm water, the Ice Age is going to start right away, but only in protected areas from the warm onshore flow. A good place would be central Canada, southeast Canada, away from the west to east flow from the warm Pacific. But it's going to delay the Ice Age in a lot of spots, like in England. You can have warm onshore flow, and so it's going to be wet and moist early in the Ice Age there, and pretty warm. And that's probably why you find 100 hippo fossil locations buried with cold climate animals in England.
And that's a helpful answer in terms of this follow-up question. So when you mentioned that us Cretaceous, we can acknowledge some paleosols, were they defined that word as ancient soils? By ancient soils, we would say during the Ice Age, a few thousand years ago.
Yeah, or landslides, or terrace floodplains. You can cover up a soil, but they'd be shallow today. They'd be pretty shallow. But paleosols are now very common throughout the geological column, even in the Precambrian, they claim. But we would dispute that they're buried soils.
Howard Feldman asks, because we're on this topic, so I guess we'll focus on the questions dealing with this. How do you explain all the different types of soils in the rock record between marine layers that match the diversity of soils today?
Well, I'd have to see the evidence that they match the diversity today. And I would have to examine how they would form in marine layers. So I'd have to look at the data, and my friends would have to look at it. This is not my forte. I'm getting my stuff mostly from Peter Kleberg and Rick Bandy,
who have both worked in the field and observed these things.
Yeah, they're going out actively looking at and writing about paleosols. Like I said, they're going out in September in southeast Montana.
That'll be good. So is there an observation that they could hypothetically make when they go out in September where they would be forced to say, okay, what Howard Feldman is saying about these so-called paleosols is true, and now we got to interpret that according to the flood model? Or at that point, maybe critics are wondering, are we going to tap out and say, okay, these do represent deep time and contradict the flood? How would we deal with that at that point, Mike?
Well, we got to find it and analyze the data, the observations, and see if they can match what a buried soil should be. A, B, C horizon, and some organic material. Now, so that's what they're finding, and some of these exotic features like slickened sides and that they're finding that first of all they're rare, and so they can be accounted for by other processes. So that's what they're doing. They're examining the data, and they got to find them first. It's very frustrating because you go to places where they're claimed and they don't see anything close to what would be a buried soil. So they're coming up mostly negative, but they got to be out there, some good possibilities. So I'll have more information from them later.
Well, and I've got a lot of notes from your presentation. Would your model therefore allow for flood sediments to base? Clearly, this is the main part of your model, that you're allowing flood sediments to become temporarily exposed between depositional pulses, during which you can have weathering, chemical alteration, give the appearance of the paleosols that we're talking about. Biological activity, that's a big one.
Yeah.
Rooting and erosion before renewed marine deposition buries the surface. So if that would so even if what he's saying is true, would that really contradict beds, or would that be something we could still account for?
Probably not. We could probably account for that, but like I say, with all these challenges, I need to examine the observations in depth. And when I do that, I usually discover that there's lots of uniformitarian problems that don't show up with a casual look at the problem. And about 50% of the time, I can usually find a way to explain the challenge during the flood or the post-flood rapid ice age. But there's still challenges out there that I can't explain. But we have a lot of explanations for challenges, a lot of great explanations that give hope that that the flood can account for all of them eventually if we had enough data and enough data.
Well, I like it. And brainstorming through the beds model and how it accounts for a lot of these features and observations, and then what Howard is saying, just kind of assuming what he's saying is true. And I'm just kind of brainstorming on the spot. You got marine deposition, temporary exposure and alteration / biological activity, then renewed marine deposition.
Yeah.
And so that presence of a paleosol-like horizon between marine layers, like Howard is saying, would demonstrate an interval of exposure. But is that really telling us how long that interval lasted? Because Howard would have to say that interval lasted a lot longer than we would say. But I feel like that is where maybe the debate would start.
With chemical changes, it could, you can change the top sediment rapidly, and then you bury it and cover it up. I think we can explain that by the beds model and the mechanisms of acid rain and hydrothermal flow.
Right. No, that's my thinking too. And so I want to pull up this question here that came up from, okay, it's along the same lines, but I think you just kind of addressed this. So we're addressing a lot all at once, with which I like. Andrew Cumming, another critic in the chat. Good to have our critics. Paleosols can't form in a matter of a few days or weeks either. But you are saying, to just kind of back up a little bit, you are saying true paleosols could form within a lot longer than that during the post-flood ice age as well.
Yeah, they can form after the flood. If those buried, I would expect them to form quickly in a matter of a few days or a week. Acid rain can react pretty fast with a top layer and chemically change it to where it could duplicate what they think is a B horizon. So I don't have any problems with that.
We got Dr. Joel Duff here. Good to have you, Joel Duff.
A lot of critics.
We've got all the critics, Mike. They've been looking forward to this. And so
thanks for coming on.
This is model building and peer review in real time, isn't it? That's what I like to say when we do these with the critics present. Real time, on the spot peer review.
Okay.
So Joel Duff has a criticism here. It looks like beds does not specify the required water depths, rates, and amplitudes of rise and fall, sediment loads, current velocities, duration of exposure, or how animals could repeatedly reach. I feel like he's basically just kind of maybe criticizing the model, thinking that it's not been thought out enough to be a sophisticated model. Is that true, Mike?
That's true. Yeah, it's a general model. Yeah, I haven't gone into any details like he's mentioning, but it's a model that it's a general model. So
but it's a general model that provides some good answers to these challenges.
Yeah, it's just got good answers and possibilities for future research.
And is that where we model build, right? Here's the general model. Here's how it can answer these challenges and observations. Now we can get into the specifics. Would there be a way to flesh this out in the future and kind of address these specifics?
Yeah, you'd have to go out in the field and find dinosaur areas. They're up on the Blackfeet Indian Reservation, where I had permission to go look at some fantastic dinosaur features. They were, I think, 3 levels, even dinosaur eggs. And so that's kind of what I think of when I think of forming multiple layers of these things by repeated exposure of beds and then covering it up, another drop, expose it again. Remember, we're talking about a big area. We're not, I just gave a kind of a snapshot, block diagram for these features showing the potential of the model.
I think people might be thinking, because of those images, you just had that little block example with the dinosaurs on there.
Yeah.
And then the flood, over here, and then eventually, but you're talking about a large area of land where this is taking place.
I tried to emphasize that. And there's a number of features on the beds that would indicate the environment of the flood. For instance, dinosaur tracks. Now, I'm an elk hunter. Hopefully I can get out there again at my age, but I a lot of times track them in the snow, and when they're feeding or moseying around, they just meander all over the place. But you spook them, and off they go in a generally straight line. And practically all these dinosaur trackways are in straight lines or gently curved. I can show pictures of this, indicating an unnatural environment. And I postulate it's because they were trying to escape the encroaching floodwaters, and so therefore they'd run in a straight or walk in a straight line. I'm not sure too many dinosaurs can run, but so there's features and dinosaur eggs. Dinosaur eggs are very porous, and practically all of them are laid on a flat bedding plane. There's hardly any evidence of a nest, a pocket dug, or with vegetation on it. You don't see these features. They're generally practically always on a flat bedding plane laid, and that is unnatural in that they're so porous that the embryo would dry out really quick. But in the beds model, you have pregnant dinosaurs that find a place to get out of the floodwaters. They get up on it, make tracks, lay eggs in a hurry. They're in a hurry. And I think the actual details of the eggs and the dinosaur tracks favor this versus a natural environment. By the way, they're always on flat bedding planes. You don't see them climbing hills, or there's no hills they climb. It's always on a flat surface. Of course, the mainstream scientists will say they're always on a beach or on a shoreline. Well, I don't know about that, but anyway, I feel that being on a flat bedding plane favors the beds model over dinosaur features over hundreds of thousands of years.
And you just answered this from Howard. He sent this in earlier, though, to be fair. What about the dinosaur nest, which obviously your beds model accounts for nicely? And so the nest, the eggs being present, tells us that those sediments were exposed long enough for those to be buried and preserved. But how long, according to the flood model, would you say? Because some people say, well, was it days, weeks, months? How long would you say on average, or what would be a good answer to that?
Variable. As far as dinosaur nests, they're very rare. There's one I've seen on what's called Egg Mountain. It's only a 50-foot high hill west of Choteau, Montana, where they do have a kind of a bowl-shaped nest with the eggs in it. But that's rare. And that's documented in some publication of mine, probably that Dinosaur Mysteries and Challenges. Yeah, I think I document that there.
Joel Duff says there are plenty in which tracks go in two directions.
Well, yeah, they can go in different directions, but they're generally straight or gently curved. So it's not the direction.
Joel seems to be challenging the argument. He says there are many articles that explore the ecology of where the eggs are found.
Well, I've read some of those. It's no doubt that dinosaur eggs are very porous. There are hardly any nests. They're generally on flat bedding planes. I mean, what more do you need to say that this shouldn't be? It should be either in a hole, or if they're on a flat bedding plane, covered up with vegetation. And you don't find the pollen on top of the dinosaur eggs in the sediments, or you don't find them in a hole. They're very rare. So I'd say that's a big problem, and that the mainstream scientists need to explore more.
As we're answering challenges, and you've pointed out in the past that it's easy to show or poke holes in the deep time evolutionary model. And so it's a lot of fun to answer challenges, but as you're answering challenges and digging into the literature on this issue, in the conventional literature, you're pointing out that you find their own challenges that they need to engage.
Practically every challenge. By the way, the Lord has led me over 51 years to answer challenges that mainstream scientists give us. Not necessarily to challenge evolution, which when I got out of graduate school, I found it was extremely easy. Just learn a little bit about the situation. You find out there's so much evidence against evolution, but he's led me to answer challenges. So that's what I've done over 51 years. And when I find a challenge or they challenge me, I go to the literature. And when I gather the data, observational data, that is, I usually find that it's a challenge to mainstream scientists also. So that's the first thing I discover. The second thing is, like I said, about 50% of the time I can find explanation within the flood or the ice age.
Looks like Howard Feldman says sedimentology, so as a further objection to what we're saying here, places strict limits on flow velocity. This was something he mentioned in a recent debate he was present here for, and depth during valley filling that do not fit the beds model.
Okay. Strict limits on. Well, I'd like to know more about that. I'd just like to look at the data on that claim first.
Yeah, because doesn't flow velocity and depth simply tell us about depositional conditions, but doesn't necessarily tell us about time scale or the history of that deposit? So how come those conditions could not, from the flood and the beds model, not, I guess, wouldn't we have to ask Howard what specific measurement quantitatively rules those conditions out?
Yeah, that'd be good to know,
beds to
first of
account it?
all. And any literature on the subject, and where are they?
Does this question make sense to you, Mike? Howard is wondering, how do you explain the many cycles of zero isotopes that match stratigraphic evidence of many glacial cycles?
The old isotopes, that's oxygen
okay.
isotopes. That is a challenge. The way I would answer it is that in a terrestrial environment, you see evidence in most places just one ice age. The cycles of oxygen isotopes are based on deep sea cores where the cores might be 15 meters, and they pull it up and they analyze variables, which the oxygen isotope's the number one variable, and they wiggle both ways like this. And when it wiggles one way, they claim it's a glacial. When it wiggles the other way, it's an interglacial. I think there's other ways to explain that data. Some of my articles have dealt with this in the past. I don't believe that they're glacial interglacial oscillations, but they're due to oscillations caused by other mechanisms. It's been a long time since I worked on this, but one way to explain it is that they're finding out. By the way, these oxygen isotopes are mostly in foraminifera carbonate, and there's ways you can explain this by depth changes of the foraminifera. And by the way, the oxygen isotope is pretty sensitive to temperature. Another way is that they found that the surface of the ocean is commonly has eddies, and these eddies maybe they're 50 miles in diameter, and they have different gradients of the variables. And so as you're getting sedimentation or carbonate sediments from foraminifer from these, you can get changes in oxygen isotope ratios, which, by the way, is not very large. The amplitude is maybe about 2 per mil, 3 per mil. So we're not talking about huge oscillations. So I think they're due to a lot of other variables during rapid sedimentation during the flood. That's how I would explain it off the top of my head from research I did done over 20 years ago.
And it's still right there for you to give.
Yeah, a little bit. Yeah, it's things are getting kind of scrambled though.
Well, you've researched so many different topics over the years. Here's a good question, Andrew Cumming. So the beds weren't yet fully consolidated, so they could be eroded back, yet they were still hard enough for dinosaurs and other animals to walk on.
Yeah. No, they would not be fully consolidated. They'd be probably compact, and so that the prints would occur, and then you be hard. Yeah, be hard enough for dinosaurs. Yeah, I go along with that.
And then that way, hard enough for dinosaurs to walk on, and then also leave their marks, their traces.
Yeah, and in places where they're too soft or too hard, you don't get good traces or any traces at all. Right. So there are, fine tuning in some of these things, which you'd expect in the beds model.
Howard's pushing back on us. He says,
okay,
the glacial, interglacial oscillations, this is going back to the oxygen isotopes question,
yes,
is confirmed by shelf edge stratigraphy, which shows many rapid cycles of sea level.
Yeah, I would wonder about that. I like I said, I'd like to see the evidence for that. Shelf edge stratigraphy. Well, if you're talking about shoreline levels with a drop in sea level, some of those are pretty equivocal. So I'd have to see the data. Sorry about that. I have to see the actual data to just have a response to this.
Well, a lot of these things you see, you got to see the data, you got to see it in real time, like you were saying.
Yeah,
a couple of your friend researchers in September, and then even in those cases, because we've had Howard say, "Hey, we'll take a group of you Cretaceous out. I'll show you these paleosols and river channels, so on and so forth." But even if you go out in the field and see these features for yourself, that doesn't automatically mean that they're right, because what they're interpreting could, again, let's say the paleosols, okay, yeah, we see those observations, we agree that they're there, they look like paleosols, but hey, that doesn't demonstrate that they were there and exposed for as long as they would say, the chemical alteration, the acid rain, the ice age.
mm-hmm.
But I guess what I'm getting at, Mike, even within the field, we see the data, we see the features. Even if we admit, yeah, these features are there, I get it, we're both looking at the same thing, that still doesn't automatically mean the apologist of deep time is right.
Exactly. Yeah, I've been out in the field with geophysicist with a PhD, and he was showing me all these planation surfaces out there and saying that's evidence of I can't remember his exact words. This is 35 years ago of a lot of time. But then when I got to looking at it, I realized that planation surfaces are not forming today. And but they can form easily in the flood due to rapid flow, planing down rough areas to a generally flat surface. So that started me on geomorphology. And anyway, he would interpret it one way and I'd interpret it another. And we were looking at the same things. So yes, I just say in this case, I'd like to see these things. And they could be legitimate challenges to the flood model, which there are. or I might be able to find a good explanation on it, and I have in the past. So I need to look at the data. Sorry about that. I have to read the articles and look at the data. I'm not copying out. This is just the way to do science.
Right. Especially once you get into the hyper specifics. Here's the general
Yeah.
model. Here's the general model for the deep time proponent. And then once you get into the hyper specific details, okay, well, let's have a lot of these questions are going to require, like earlier with the flow velocities. Okay, well, we're going to need critics to quantify it and show us a little bit in more detail what the major issue is that apparently would preclude the flood. I'm curious as to your thoughts here. Howard says the oxygen isotope cycles are consistent worldwide, and now he's comparing them to magnetic reversals.
In deep sea cores, I'm not sure that they are consistent globally. But the magnetic reversals are almost independent of these oxygen isotope ratios. If you look at if I understand this correctly, they date by biostratigraphy and magnetic reversals. And let's see, that a physicist from ICR, I can't think of his name. Anyway, he documented a situation where the last reversal was dated 780,000 years, Bruns Matayama, and it was used to, first of all,
is that Dr. Jake Hebert?
Yeah, Jake Hebert. It was used to document the pacemaker paper, and then they did a spectrum analysis and got the nice Milankovitch cycles, which I think there's a lot of circular reasoning going on in all this. And but they redated that magnetic reversal to 700,000 years, and Jake Hebert ran the calculations again and did not get 2 out of 3 of the Milankovitch cycles. So I think there's a lot of circular reasoning going on, making these cycles and the dating of them all fit preconceived ideas of the astronomical theory of the Ice Age. I think that drives a lot of what I would call post-flood features from deep sea sediments that can be from the ice. A lot of them are from the Ice Age, ice cores, and probably other things. Anyway.
Well, the other big one, I've got some questions on this, so I'll just lay it out first from my own words, and then we'll bring in some of Howard, and I think Joel Duff has a few things on this too. But the river channels, one specifically, it was a challenge that Dr. Howard Feldman brought up in response to Dr. Tim Clary, his presentation and answers on the issue. But he points to river channels and formations such as the Morrison that he argues demonstrate prolonged erosion in long-lived river systems. And I see this same argument, especially on Facebook when we post the reels from these programs, whereas Cretaceous will point out the general picture, lack of erosion, fine boundaries, pancake layers, so on and so forth. And they'll usually respond and say, oh, wait a minute. No, we do have the erosion. We have the river channels. And then someone like Dr. Feldman points to this example in the Morrison. Mike, what's a good response to that?
Okay, specifically in the Morrison, we're talking about what he determined as river channels. I'm not sure of the question.
Yeah, would that act, if there are legit river channels, would that demonstrate long periods of time to form?
Well, first of all, I'd question whether they're really river channels or channels carved during channelized flood erosion. So that'd be the first thing I would question. And as I showed in that series of 5 slides,
Yeah.
you'd expect channelizing of beds as the floodwaters drop. You went from wide flows to more channelized flow. The channelized flow will cut valleys. So I would explain it that way, but like I said, I need some details on that one too.
So the flood model would therefore predict localized erosion and minimal channel formation?
It would localize erosion, but it would predict channels would be formed on freshly laid sediments. The channels would be could be carved through that as the level of the floodwater is dropping, and they can form rapidly because the sediments are probably fairly soft and unconsolidated mostly, and so the erosion could occur very quick.
So those processes would naturally carve channels quickly before later sediments fill and preserve them for us to see, and then the evolutionists interpret those as
Yes.
requiring deep time.
Yes.
Okay.
So
So
they get filled in and covered and buried and so forth.
were there rivers and river channels pre-flood that would have been buried?
Oh no, I think the pre-flood world was just totally destroyed. I can base that on the amount of sediments that were generated during the flood, based on the amount of sediments in the ocean, which would the vast majority be due to flood runoff, and so it eroded the top levels of the sediments, and then the sediments added. You got a huge amount of sediments deposited early in the flood up to day 150. And so that amount of sediments implies a huge amount of erosion. And so any pre-flood topography, anything would be totally destroyed.
So for anybody who's brainstorming ideas on how to answer all these, it wouldn't be a good idea to say these are pre-flood features. No, these would have to occur during the flood.
Yeah, the flood was so violent.
Yeah.
It destroyed so much, eroded so much. And me and a team have been analyzing the sediments, where the sediments are and what they mean. And based on the sediments in the ocean, which average 3,000 meters along the margin, up to over 18,000 meters. No, is that? No, yeah, 18,000 meters, 18 kilometers. That was mostly from flood runoff. But when you bring that back up onto the continents for the peak of the flood, that's about 1,900 meters. So we've concluded, based on the GlobeSed project that determines where the sediments are in the ocean, that you eroded the top of the sedimentary layer an average of 1,900 meters for the receding stage of the flood. So that 1,900 meters was deposited earlier in the flood on top of what's left after the erosion, which is somewhere around 1,500 meters, I think. We're getting variable numbers depending on which state. So the total sediments you need at the peak of the flood at day 150 is about 3,500 meters, average on all the continents. That's a tall order.
Wow.
And it says a lot about the early flood, how catastrophic it was. And so we still have a lot of explaining to do in coming up with that. 3,500 meters average on all the continents. And this is what the sediments are telling us from their locations. So the upshot of this, getting back to the original question, is that any pre-flood topography, anything is going to be totally eroded and destroyed.
Interesting. Well, that's helpful then in interpreting some of this data. No, these are features formed during the flood, but as you're putting it, the flood wasn't uniform. It was multi-dimensional,
Yes, very.
multifaceted. There's a lot of
Yeah.
different phases, really catastrophic at the beginning stages.
Yes,
And
especially.
eventually you have the recessive stage of the flood, which you've done at least 2 presentations here. And
Yeah.
so a lot of these challenges, I think, could simply be answered with a proper understanding of the dynamics of the flood. When Dr. Feldman was here for a few times during our open panels and then the debate itself, in response to a question that I had asked him regarding the local channeling that could take place during the flood rapidly, his response was, well, ancient river morphology matches modern rivers and therefore formed gradually over long periods of time. That was his counter to our position that might say, okay, we can get some localized channeling quickly.
Well, how come there aren't any tributaries, as they admit, to these channels like you'd expect in a normal drainage pattern? That would, I think, would be one problem. So anyway, and we've gone round and round on this. I think they can be formed in the beds model, and he has evidence that there has to be slow. It would be nice to look at some real good details of all this stuff.
I don't see how similar because you can get similar characteristics that either form slowly. I mean, you can look at all kinds
Yeah.
of data, biological, genetic data, like mutation rate data. You can get a lot of DNA differences quickly in some lineages, or you can get them slowly, but you're still looking at those DNA differences. Same thing with these characteristics of so-called river channels. Either you can get those characteristics quickly, like during the flood, or slowly. I'm not quite sure how that observation would differentiate between the models. But Andrew Cumming is wondering, I think this is a good question
It
because
is.
we talk about model building, multiple working hypotheses. We don't have all our cards on one single position. You've talked about the importance of multiple working hypotheses, but the gold standard of science, of course, falsification. So Andrew's wondering, would any observation falsify the beds model according to Mike Oard?
Oh, good question. I can't think of anything, but the same applies to the mainstream view. I don't think there's probably any observation that would falsify their view either. So we both are in the same boat of unable to falsify or even present falsification criterion for our models. Because I've read a lot of mainstream geology stuff. Like I said, I try to keep with 50 Earth Science journals. I'm having a hard time because I'm working on projects that take a long time. And they run into problems, but they explain them away by alternative hypotheses. That's commonly what I read in the secular literature. So I'd say their ideas to them would be unfalsifiable also.
It's a good point. They're always accommodating the data. They're always employing rescue devices, especially when it comes to the genetic evidence that contradicts the idea that humans and banana plants are related. So one could say the evolutionary model is unfalsifiable too. Here's a question from a new commenter here. A lot of engagement. I'm really trying hard to multitask here, Mike. There's a lot going on in the live chat. So this question, you had mentioned the flood boundaries earlier. Well, in the context of the coal, you find these massive coal beds that would require what we would argue are catastrophic flood conditions. But I think a lot of these coal beds are found in locations that some creationists might say are post-flood. So that's interesting. But this question says, you are both excellent. Well, I appreciate that. Are we further along the process in proving that the flood boundary is at the upper Pleistocene? Dr. Ross thinks it's lower. So I think that comes down to the high Cenozoic and variable model that you point to. And then other creationists say it's lower at the KT boundary.
Oh, yeah. I've spent a lot of time on this subject. First of all, we don't say the flood boundaries in the upper Pleistocene. We generally would say, Clary would say that it's mostly at the Pliocene, Pleistocene. I don't specify because I think it's variable from place to place, and I can't pinpoint it in the geological column. So I generally say in the late Cenozoic, and I have 35 criterion to show this, which I think practically all of them are powerful evidences that the post-flood boundaries in the late Cenozoic. Often, though, I go along with Clary, and that's the Pliocene, Pleistocene. But I have found indications where it could be in the Pliocene in some locations, and in the lower to middle Pleistocene in other locations, but never in the upper Pleistocene. And when it comes to the Antarctic ice sheet, that is Oligocene, and that's certainly a post-flood feature, but it wasn't always Oligocene. It was generally dated as Pleistocene, but 50 years ago, they tried to match it with some fossil occurrences and what they think are, ice-rafted debris in Oligocene sediments around Antarctica. So they said the Antarctic ice sheet had to be there. So suddenly, overnight, the Antarctic ice sheet increases in age 10 times. So there's a lot of finagling in all that. And so that to me is obviously post-flood. I'd also say the marsupials of Australia are obviously post-flood. And the upper boundary in the locations only where you find the fossils, which is a very small area, the upper boundary would be in the late Oligocene in those cases. So what I'm saying is that it's variable depending on the location. You got to examine every location on its own merits for where the post-flood boundary is. But so anyway, I've worked on this 35, 40 years, and I have between Dr. Tim Clary and myself, we have at least 35 criterion to say that it's in the upper Cenozoic, a lot of times near the Pliocene, Pleistocene. I hope that answers that question. Dr. Ross, that must mean Hugh Ross, or no, wait, that's Marcus
Ross, yes.
Yeah, he thinks it's lower based on mammal fossils mainly. That's about their only argument. They have some other geological arguments, but they're not emphasized. The fossil evidence, I've come to the conclusion that there are organisms that lived before the flood that are very similar to organisms that lived after the flood. And that's what I've concluded from my analysis of the boundary, mostly from a geological point of view. So you can have boundary crossers, and they could be the same genus even, genus being having a certain amount of variability, and you can have some variability from a pre-flood organism to a post-flood, but it could be almost exact. I don't see a problem. I wouldn't expect that to be, I'd expect that to be rare. So that's what I've deduced. And talking about fossils in the lower boundary, if the upper flood boundary was at the Cretaceous Tertiary or Cretaceous Paleogene, or even in the early Cenozoic, as some of them say, then we have the peculiar situation in flood geology that the flood buried very few mammals, and yet after the flood in the Cenozoic, we buried millions of them and fossilized them. Now that is so anomalous that to me, that's one of our main 35 arguments that the Cenozoic, most of the Cenozoic is from the flood. Also, if you look at the details of the mammal fossil record, you have hundreds of first and last appearances that are precise globally. I think there's a lot of circular reasoning going on in making that claim by the mainstream scientists. But someone who believes the Cenozoic post-flood would have to explain all that after the flood, and I think that's impossible. So I think the fossils indicate an upper flood boundary in the late Cenozoic. But anyway, for the skeptics listening, this is an in-house flood geology controversy.
Right.
So, and we're still working on it.
It's a fun controversy.
Yeah, it should be, but like all controversies, I try to use charity and try to listen to their arguments first before I respond. And so sometimes opinions can get pretty
lively
lively.
in the most professional way.
Yeah, right. Okay.
Intense in-house discussion,
Yeah.
as we all
And that's the
model.
way I would respond to the critics on this. We can have good discussions as long as it's in charity.
Amen. So there's a follow-up here, and before I read it out, you've spent a lot of time here. Going back a few years ago, we did a whole series, pre-flood boundary, post-flood boundary, and then I think we did a whole third program just kind of addressing issues, objections, so on. So there's like 6 to 9 hours of content there for people to enjoy on that. And so there's a follow-up here, and they're wondering, but the Gibanium layer in the upper Pleistocene is very thick, 3 kilometers in Japan, for instance. So that has to be from the flood, right? Therefore, upper/newest Pleistocene must be flood.
Okay, I didn't know about that. I'd like to know more. But yeah, I don't think 3 kilometers of sediment can be deposited after the flood. So I would definitely say that would be from the flood. And if it's dated upper Pleistocene, yeah, I would put that in the flood. I have no problem with that because the Pleistocene is just a category like the Pliocene, Miocene.
Right.
And it does not necessarily mean it's ice age. Maybe the very upper Pleistocene in some spots it's ice age, but other places it need not be, because there's some thick Pleistocene sediments in places like the South Caspian Basin. So yeah, I don't have a problem with that.
Does the Pleistocene, according to the geologic rock record or the way they interpret it, is the Pleistocene in the upper part of the Cenozoic framework?
Yes.
So it would still work with upper Cenozoic, but variable, as you've argued.
Yeah, it still comes into the late Cenozoic. The late Cenozoic is defined as the Miocene, Pliocene, Quaternary. The Quaternary is mostly the Pleistocene with a little Holocene at the top. And in some locations, it could even be in the late Oligocene, which would be the very late, early Cenozoic. And like I gave examples of the Antarctic ice sheet and the marsupials in Australia. And you can read some of the literature articles on creation.com on those topics.
For a lot of that strata to be post-flood, you'd have some major catastrophic local events then post-flood. I mean, you have this worldwide flood, and then for 1,000 years or so afterwards, you have all these like mini, almost worldwide floods too. Rather than, I think with your model, you're putting it all in the flood, which makes more
why
sense.
not? The flood is designed to be a global catastrophe. And when you get thick Pleistocene sediments, they got to erode from somewhere, not just from the local. It's probably a regional or semi-continental area that would collect it. So you're talking about flood-like catastrophes after the flood, and so that I don't see.
That'd be tough as species are moving out and adapting and varying, and
that's right. You got to have the
rekindling of
animals
culture
spread all over the earth, so you can't have these huge post-flood catastrophes as the animals are spreading out. I mean, why would God do that? First of all, He would, He encouraged them to spread globally, and you don't think He's going to have some huge catastrophes to to stop them and bury them in thousands of feet of sediment.
They just experienced that for the last year, roughly. Now it's time. Now, obviously, we understand local catastrophes, of course, but it's the scale is the issue.
Yes.
And Sakaro says, thank you very much to the both of you. God bless. Hold the line. Amen. We appreciate that encouragement. And so in several of the reels that I posted on Facebook featuring you and Dr. Tim Clary, Dr. Andrew Snelling, a lot of these seminars we've done, we've pointed out that it's these sedimentary rock layers that extend over entire continents, these pancake stacked layers with fine boundaries, little to no erosion. And Dr. Clary's work on the mega sequences that correlate worldwide. On Facebook, we had somebody who is an expert in one of these fields related to geosciences. And he said this in response to that argument, Mike. He said, scale is a mundane issue. Continents scale sedimentary layers, flat stacked strata across vast regions, and mega sequences traceable across continents are all products of the fact that the earth is really big. And then he goes on to give how big some of these sections on the earth is. So he's basically saying, according to the old earth model, what we find here that we interpret, Mike, as being the result of the worldwide flood is also expected in the deep time model. I'm curious as to your thoughts. Is that just them kind of accommodating it, or is that a valid point he has?
Okay. Let's talk about Cambrian sediment, sandstone. Now, we usually use the Grand Canyon as the type road cut. Anyway, the Tapete sandstone was 100 to 300 feet thick of almost pure sand. I've viewed it in several places. And this sand can be traced over half of North America. It can be found up in my area of Montana and Wyoming. It's called the Flathead Sandstone. And it sits at a unique location, so you can't miss it. It's usually on the upper crustal rocks, granites and gneisses, usually the great unconformity below it, representing a time gap of 1 million. And in Wyoming, it's a time gap of almost 2.5 billion years. It's generally flat. The Cambrian sandstone's on it. And you can trace this sandstone, like I said, and you can see some maps by Tim Clary and Andrew Snelling through most of the United States to the Appalachians, up through parts of the Canadian Rockies, up into the Queen Elizabeth Islands. And this is what you expect in the flood. In a secular model, and by the way, I'm getting this from Dr. Feldman, is that sand originates from rivers, and then from the sand, the sea level increases and moves the beach far inland. However, that explanation has a problem because river deposition and then beach deposition, you change facies, that is rock sediment types, quickly, laterally and vertically. But this is a layer of almost pure sand, 100 to 300 feet thick, covering half of North America. To me, that's a huge uniformitarian mainstream a challenge. And I don't see how river deposition or moving beaches could possibly account for such a feature. And then when you look at the other layers in Grand Canyon, they're flat one on another, showing little or no erosion between layers and within layers, and yet it's a sequence of 250 million years from the Tapete sandstone to the Permian Cape Kaibab limestone. The significance of that is that erosion on a 1 million year timescale is so fast that at the present rate of erosion, you can erode all the continents of the world to sea level in only 10 million years. but that's a maximum because as the relief decreases, mountains are eroded, the erosion rate actually decreases. But a number of secular scientists have put maximums on it. And I get one I've seen is 33 million years to erode all the continents down in a more realistic time frame. I've seen other ones, but I usually say 50 million years. So if you can erode all the continents to sea level by the erosion on a million-year time scale in 10 to 50 million years, where is all the evidence of erosion in any layer, sedimentary layer, which are practically globally one layer flat on another with little or no erosion between the layers and within the layers? To me, that's a huge challenge. They might be able to point out some features at the boundary of that indicates some time, but when you're talking about hundreds of millions of years, I don't think that explanation flies. So I would consider that their biggest challenge when it comes to sedimentary rocks. Are the how far they go, the grade area, especially the Tapete sandstone and the flat layers between them, which are global sequences, they're globally like that. You might find some little erosion marks here and there, but in general, they're flat like pancakes. And that doesn't fly well with the hundreds of millions of year time scale.
If my wife came down with a stack of pancakes, she put one pancake, the first pancake a week ago, and then the second pancake just today, I'd be able to tell. There's been a lot going on with that first pancake. I probably don't want to eat it.
Yeah.
And so these pancake stacked layers, you'd expect more evidence for the deep time or the millions of years between them. You'd be able to tell. There'd be features we'd expect to find.
Yes.
Mike. So what if they say, well, the geologic record is filled with unconformities, Mike? These are breaks between formations signifying millions of years of the erosion that we say doesn't exist.
Well, there are those, of course, but a lot of areas you don't find anything except for para-unconformities, which are just differences in the time scale, or disconformities where you find a little roughening of a surface. But you do find angular unconformities, but this can be explained by tectonics. You deposit sediments, you have tectonics, it bends, roads off, more sediments are laid, and so you can have angular unconformities here and there, but you don't have a lot of them. And but most of the sedimentary rocks look like a stack of pancakes, no matter where I see them. And I think this is a global pattern. And of course, there are various types of unconformities, and I don't think these are a problem. You can account for them in the flood.
It's the global pattern that suggests a global catastrophic event.
Yes.
Howard says, there is lots of evidence that many mountain ranges have been eroded away. All we have is the sediment shed from them and the mountain cores.
Yeah, that could be true. I've heard that like the Grenville orogeny is supposed to be as high as the Himalayas, and they got eroded down to just the roots, and the sediment spread, especially westward, sometimes 2,000 or 3,000 kilometers, by the way. Yeah, that could very well be have occurred in the flood. I have no problem with that. I'd like to look at the data a little more. I think the evidence of orogeny in some places are just thick sediments, but I need a little more than that. But I would generally say go along with this.
So would that be the same observation, but we're explaining it through rapid plate tectonics
Or
rather
rapid,
than
rapid mountain building and then
Mhm.
rapid erosion. Yeah, I think you'd have a lot of that because especially the Precambrian was extremely deformed and a lot of tectonics in the Precambrian. When you get to the Paleozoic, you don't see a lot of tectonics in like the sediments in Grand Canyon or the Grand Staircase. It looks like I call it the Great Deposition, where after this huge tectonics in the Precambrian, things settled down, and then it was quiet, generally quiet sedimentation for early in the flood. One layer laid on another, getting 15,000 foot sequence in that area of Arizona and Utah. So, and you can have, I could see you could have mountain ranges that come up from various regions due to tectonics and get flattened and sediments dispersed. So, I mean, I think that's it's a reasonable model to think about, but I say it all but can occur fast in the flood.
Right. So I'm understanding that even if hypothetically Howard showed us the data, even if we're in the field, it's not like, oh, we see the data and it's exactly as Howard has presented it. That doesn't mean it now precludes or contradicts the global flood model. We have
Exactly.
explanations. But at
Yeah.
the same time, we still want to see the data because are we invoking an explanation that isn't necessary because the data is not necessary, right? But if we do see the data, okay, hypothetically, well, here's a good explanation for it.
Yes, that's exactly right.
There was one here I want to, oh, here we go. L. Drosophila, fruit fly. What about Aeolian sedimentation?
Well, look at John Whitmore's research on Answers Research Journal, and I think it'll open your eyes that these so-called Aeolian sediments are not windblown sediments. There's a lot of evidence that they're laid down in water, like the Coconino sandstone. For instance, you have feldspar that in a hundreds of thousands a year, millions of years framework should weather quickly. You have mica, and I think and you have other features and the cross beds are not huge like you find in windblown sediments today. So they compiled a huge amount of evidence. So look on the Answers Research Journal, John Whitmore and colleagues, for an explanation, an alternative explanation for these Aeolian sediments. We have a lot of them in the West here claimed. It's always interesting that the paleo flow directions are practically always from the north, which is rather odd for multiple deserts. And they have so-called desert sediments in many ages here in the West, mostly the Permian and the Triassic and Jurassic. You have the Jurassic Navajo sandstone, same thing, the Permian Coconino. Anyway, look at that. That's some good research that this person, you should look closely at. I don't know, it was published 2012, 14, something like that. It's on the Answers Research Journal, but it's a very long article and very detailed and definitive, and it's top-notch research. So please look at that for our explanation for so-called Aeolian sediments.
Yeah, I'm looking it up right now, and there's a few articles and papers there. But so John Whitmore, excellent research, like you're saying. His research on the Coconino, he's basically saying, well, the Aeolian sedimentation is more of an interpretation. It better fits the underwater deposition.
Yes.
Better than desert dunes.
Yes.
And he's looking at crossbed geometry and grain characteristics. He's looking at a number of things to come to that conclusion. He's not just, yeah, that's powerful.
Lots of different things. It's a long article. very, very good. I recommended it to anyone who still believes that there's Aeolian sediments.
Andrew Cummings wondering about the Navajo sandstone, for example. Is that difficult for us to explain?
No, I think it's the same thing as the coconino. In Zion National Park, it's what, 2,000 or 3,000 feet thick. That's a lot of sand.
That is.
No, I think that's just one of the sands in the western U.S. that is, you can show it's laid down in water. I think that Whitmore and others have been doing research on that, but I haven't seen anything definite. I've seen it in a lot of different places, and I just go along with it. It's like the Coconino sandstone, but just dated younger. So it's just one of the many claimed Aeolian sandstones in the western U.S. There's quite a few of them claimed, but all coming from the north, which is rather odd. What's up in the north that would produce all this sand? British Columbia, Alberta. I don't think there's a source. They have a source. Now, of course, we don't know the source either, but we believe it's a flood laid down in water deposit, not Aeolian.
Nivalian's wondering, does Michael J. Oard agree more with Dr. Tim Clary's model? I bought his book, Carved in Stone. That's a great book. I got it right behind me, and is very interesting.
Well, Tim and I agree on a lot of things, but we have our differences of disagreement.
No two Christians are going to agree on 100% of everything. That's for sure.
That's what makes flood geology. See, flood geology, as you critics know, for us to explain all this stuff in the flood can be difficult. You know, you have some good challenges, and I don't mind good challenges. And so, as flood geologists, we look at it, and sometimes we come up with different solutions. But like I said, Tim and I mostly agree on most aspects of flood geology. But like all of us, we have differences of opinion in certain areas. Like the biggest issues are, where's the upper flood boundary? Where's the lower flood boundary? Those are two of the major issues that we have. But it's an in-house discussion. We're doing research and having discussions and debates about it and writing papers. So, but in general, we agree on most things.
Right. We agree on the bigger picture. When we're answering challenges or looking at the details, there's going to be differing opinions as we model build and we hold to multiple working hypotheses. That view, but you find the exact same thing in the world of evolution in the conventional literature. When I'm studying paleoanthropology or looking at fast mutation rates in mitochondrial DNA that go right back to roughly 6,000 years for mitochondrial Eve, there's in-house debate directly in the conventional literature. How do we explain this? Maybe this. And then another author of another paper is saying, no, that doesn't work. Maybe it's this. So there's in-house debate wherever you look.
Yeah, that's the way science works.
Right. That's a good point. If there's no in-house debate, that could be a bit odd.
Oh, dinner's come.
Oh, Mike, you've earned yourself a good dinner. So I think that right there's a good line of evidence that maybe we'll start winding down here so that dinner doesn't get cold, brother. You've done a great job here. It's kind of been a rapid fire Q&A, hasn't it? I mean, it's been you taking on all the critics, and I've really enjoyed it. You've done an excellent job. And so you've earned yourself the rest of the night off soon. So maybe I'll sneak in these last couple and then we'll wrap up. 2 hours has flown by, Mike. Doesn't feel like it. So
yeah.
Al Drosophila is wondering, and we've discussed this, so feel free to provide a summary or nutshell answer about the limestone. There's a lot of videos out there, anti-young earth creationist videos, that in a nutshell say there's just way too much limestone on the planet to explain in a young earth global flood timescale, Mike.
Yes, there is a lot of limestone. I think it's about 20 to 25% of all sedimentary rocks are carbonates, not necessarily limestones. I think about half of those are dolostone. especially the earlier rocks are mostly dolostone, but I think 4 times as much than limestone, Precambrian rocks I'm thinking of. Now, to form dolostone, you need temperatures over 100 degrees centigrade for primary deposition, which is difficult for a mainstream scientist to think about. And so they're always trying to say, well, it's limestone that's been replaced by dolostone. But you look at the data, it doesn't really fit very well. But just the amount of carbonates, that's a good challenge. There's way too much. And therefore, I believe that much of it, or practically all of it, came from the fountains of the Great Deep, from below the ground. What evidence do I have? Well, there's evidence of carbonate lava flows where 50% of the lava is carbonate, a carbonate mineral. And they got names for the carbonatite. And there's, I think, something around 500 volcanoes that have given off this carbonate. And this carbonate has to come from the subsurface. So there's a lot of, must be something down there that produces the carbonate. And so during the fountains of the Great Deep, I believe you had a lot of hydrothermal flow of carbon-rich water, carbonate, that accounts for the volume of carbonate, mainly limestone and dolostone. So that's my quick answer on that.
I like that answer. So a lot of it, like for a lay person who just wants to give a quick answer to a critic, maybe they're out having discussions, is the what took place when the fountains of the Great Deep broke open, the chemicals released, the processes associated there that's like a ripple effect to explaining a lot of what we see.
Yeah.
I like that. I like that answer. Mike, Sakero, $7 super chat. I appreciate the support and all the engagement tonight from critics and non-critics. Mike, you did not disappoint. There's been a lot of interest and excitement for tonight's program. It's been great. So he's wondering, what's your take on Jack Cuozzo, the dentist who believed Neanderthals are the patriarchs who lived to 300 years old? He's not much discussed lately. So his hypothesis, where he looked, I think, a lot of the dental features of Neanderthal and concluded that they lived hundreds of years old.
Yeah, I'm familiar with it. I think it's a reasonable hypothesis. He passed away, 15 years ago, and therefore he can't really develop his model any further. But it's reasonable. But I think it's got some problems. I'm not too up on it. I think one of it is you might see the Neanderthal features, which he believes are from old age, like the brow ridges and the fact of the skull going back further and chinless. If I recall right, you see these features in Neanderthal children, but don't hold me to that. And that would be kind of a problem for Cuozzo's model, but it's a reasonable model that can be refined and worked on. So yeah, it's, I must say, I've spent some time on Neanderthals in general, but I haven't really gone into his hypothesis very deep, but I consider a reasonable idea worthy of further research.
Yeah, and we know with good evidence that Neanderthals were very much robust, a lot more robust than us. And
yeah, they actually had a bigger volume than modern man. Not a lot. They had those unique facial features, but I believe from the neck down, they're very similar to modern man, except the bones were stronger and the muscle attachments indicated that they're very strong people. So there was those kinds of differences, and that probably fits with their ice age environment, living in caves pretty well. I mean, to survive during the ice age, predators and horrible weather, you had to be pretty intelligent. So Neanderthals were pretty smart. And by the way, DNA is showing that we all have Neanderthal DNA in us. Every single
Yep.
one of us. Some more than others, up to I think 4%. So the Neanderthals was just a people group during the Ice Age that actually had similar features as Homo erectus, I might add, that were subsumed into modern people with time. So we share DNA.
Which is a problem to those in the old Earth world that want to say that Neanderthals were non-human. We have their genetics, which means we were interbreeding with them. They're a sophisticated people group, buried their dead, navigated in the open waters for tuna, evidence for
Yes.
spirituality, made musical instruments. Hard to believe that a people group like that would not be made in the
Yeah.
image of God, eh, Mike?
Right. That's why I strongly disagree with Hugh Ross on that idea that the non-human. I think that's one of many, many problems with his beliefs and organization.
And you did a review recently of his newer book on the flood.
Yeah, I did.
We put out a clip because I asked you about that review, and you gave us a really good breakdown as to the major problems with the Hugh Ross view.
Yeah.
So I'll wrap it up with this question so we can get you to dinner. Mike, this has been great. And for a future program, we could always, continue addressing just the innumerable questions that came in to keep us busy till the second coming, probably. So Dr. Joel Duff is wondering about mud cracks. What about mud
Okay.
cracks in layers on top of another layers with different mud cracks on top? So just stacks and stacks of mud cracks with varying degrees, I guess, of mud cracks. Is that explainable from the flood, Mike?
I'd like to see it, but I think in the belt supergroup, which outcrops near where I live here in Bozeman, Montana, there are multiple layers of ripple marks and mud cracks. From the researchers on the belt supergroup, they've come to believe that those are cineresis cracks formed underwater. So I think in those areas, you got to first of all prove it's a true mud crack exposed to air. Otherwise, it can be multiple cineresis cracks during heavy sedimentation due to chemical changes in the water. And that's what they're explaining these features in the belt supergroup, which I've seen a number of them, by the way.
So with the flood, because you've been putting forth all night a dynamic, multi-dimensional flood model that would have
Yeah.
fluctuating water levels in this context could produce multiple cycles of deposition, then exposure, cracking, and then reburial.
Yeah, sure.
I like it. Well, a bonus question just came in super chat. So I guess this will be our final bonus question. Sakaro, $10 super chat. Well, thank you very much for the support. Much appreciated. The last thing he says is God bless your wife as she came in and brought you a beautiful dinner there. So enjoy dinner after this final question. We'll go with a bang here, Mike. So he said, Bible says water's covered 20 feet above highest areas.
Mhm.
Wouldn't this apply? There could be pre-flood remains, human and ruins, mega monoliths, for example, since no room for layers.
Well, like I was saying, the flood was so catastrophic, so much erosion that I don't think you'd find any, or you might find a few traces of humans, pre-flood human remains in sediments. I don't think you're going to find much because it's so destructive of pre-flood environments and habitats.
Well, Mike, that's good. That's good. This has been an excellent, comprehensive program. I like to dig as deep as I can into these. There's a lot of information for us to digest and absorb. So I look forward to re-listening to your presentation and then thinking through some of these objections and challenges that have come in. We've got just dozens of questions, but I do think we we're able to set the foundation with your talk, and then engage enough of the challenges to show that we got a good working model here in terms of beds, briefly exposed diluvial sediments. So I love it,
Yes.
Mike. Mike, I appreciate your time, your energy, all the work that you've done. You're a true blessing. And I love the fact that you're always willing to uphold the truth of biblical creation and take on the critics and the challenges, brother. Any final words and final thoughts as we wrap up our program here addressing the strongest objections to flood geology?
Yes, I would like to thank the critics for being on this program, and for those critics that will look at it later. I appreciate it. I'm not afraid of criticism. I think we need to discuss these things in charity, and we can learn from each other, kind of like iron sharpening iron. But I hope you critics could be open-minded to for the biblical flood that can explain many features which we pointed out throughout 60 some years of creationist technical literature from creation.com and Creation Research Society, Quarterly Answers Research Journal, Journal of Creation. We got a huge amount of literature. Some challenges we've answered, I think, that are really challenges to uniformitarian geology, but you do point out some good challenges for us, and I appreciate that. And I hope I don't insult you when I say I consider them research projects.
Which means they're good for business.
Yes. And
The
I have a
business
lot
of
of research to do.
There's just not enough time in the day. 24 hours in a day really isn't enough.
Yeah.
We're thankful for the critics because their challenges give us the opportunity for research projects and doing live broadcasts just like this. So you mentioned the years and years of research you've done and work. Therefore, the last thing I want to say is encourage people here in the live chat. Check out Michael J. Oard's articles here on creation.com. There are a lot. Trust me, I've taken a deep dive into many of them. Your website right there, a lot of helpful resources. Our website where you can see all of Mike Oard's very many presentations and live Q&A sessions here, and Biblical Geology 101, which I have behind me alongside Dr. Rob Carter's Biology 101, I believe it is. So yeah. Excellent material there. Mike, you've earned yourself a good dinner. Thank you so much for your time, your research, excellent presentation. We'll chat soon. To the audience, I hope you enjoyed this as much as I did. Thank you so much for your support, your engagement, and thank you to both our critics and non-critics for your questions and challenges. God bless you all. Standing for Truth is signing off.
Okay.